In a warehouse on the edge of the Baltic Sea, a stainless steel rack slides slowly along a rail. Behind it, the air is thick with smoke, heat, and silence. Each salmon fillet has already begun a journey that no one will see, not in markets, not on menus, not even at the port, because the logistics of smoked fish begin long before the first crate is sealed. They begin here, where the chemistry of preservation meets the physics of temperature inertia. What looks like a culinary process is actually the first act of a highly synchronized operation, where every thermal shift, every layer of packaging, and every second of exposure sets off a chain reaction. The mission is invisible, but it is precise. Unlike fresh fish, smoked fish doesn't just need to be kept cold. It needs to remember heat. It carries with it the memory of smokehouses reaching over 70 degrees Celsius, followed by abrupt cooling, vacuum sealing, and storage. This complex thermal layering transforms the cold chain from a passive refrigeration line into a reactive, adaptive environment. Every phase of this chain, from the factory floor to the refrigerated truck, is not just preserving a product. It's managing a series of thermal echoes, each one capable of awakening microbial risks if mishandled. The result is a kind of thermal choreography where refrigeration isn't static. It thinks, it adjusts, it absorbs shock. To understand this logic, it helps to borrow a metaphor from far below the Earth's surface. In deep mining operations, conveyor belts don't simply carry rock. They carry risk, moisture levels, timing of loads, and vibration must be coordinated with millimetric precision to avoid collapses or system failures. A similar kind of synchronization governs smoked fish logistics. Inside a container, maintaining stability isn't just about temperature. It's about moisture retention, vibration control, and air circulation, conditions that must remain steady across borders, altitudes, and climates. One misalignment, one uncalculated delay, and the equilibrium begins to shift. The risk is silent, but it's real. And that brings us to a recurring question in the industry, one that confuses even experienced exporters. Why do two identical shipments, treated the same way, arrive in such different conditions? Why does one lot show spoilage and the other doesn't? The answer lies in something rarely discussed outside of advanced logistics labs: residual thermodynamic imbalance. In simpler terms, it's how heat and cold distribute unevenly through a stacked load. Pallets placed too close, airflow channels blocked by packaging, or a subtle variation in how a crate is wrapped can all cause internal hotspots. Pockets of imbalance invisible to the naked eye, but capable of triggering condensation and microbial activity in just a few hours. Inside the crate, however, another silent hero works behind the scenes. Layers of packaging material, often overlooked, act like mechanical shock absorbers. They delay the moment when heat penetrates. They slow down microbial activation. They buy time. In logistics, that's often the only currency that matters. These thermal buffers don't just preserve, they protect. Like gaskets in an engine, they absorb stress, isolate instability, and create a margin of safety. And just like in an engine, when they fail, the entire system pays the price. This is where smoked fish stops being just a food product. It becomes a case study in applied physics, engineering foresight, and agricultural intelligence. It is no longer a matter of freshness, it's a test of synchronization, because transporting 5 million tons of smoked fish each year isn't about cold. It's about control, not just of temperature, but of time, airflow, structure, and consequence. In this system, nothing is neutral. Everything reacts. Everything has weight. Everything moves. A crate of smoked fish may seem inert, sealed, cooled, and ready for transport. But inside that crate, something is always happening. Not visibly, not dramatically, but thermodynamically. What most people don't realize is that smoked fish logistics are built on a fragile chemical balance, and that balance is in constant negotiation with its environment. Unlike raw fish, which spoils rapidly in the absence of cold, smoked fish carries within it a deceptive sense of stability. The preservation process has already been initiated, yet that partial preservation conceals a vulnerability far more complex: the vulnerability of transition. The logistics chain of smoked fish is punctuated by moments of pause: the truck that waits at the loading dock, the container delayed at port, the customs checkpoint without a reefer connection. These moments are more dangerous than the journey itself, not because of total temperature rise, but because of microclimatic oscillations, brief, often invisible shifts that disturb the internal equilibrium. During these intervals, surface dehydration begins. Moisture condenses, evaporates, and recondenses in uneven layers, creating textures and microbial environments that were never part of the original design. And when the shipment arrives days later, it arrives not just with mass loss, but with a fungal imprint that often begins before it even left the warehouse. This is where most transport plans fail. They rely on the idea of constancy, of distance, speed, and a maintained average temperature. But what truly damages smoked fish isn't always heat, it's fluctuation. A journey of 3,000 kilometers at a stable 7 degrees Celsius may look ideal on paper, yet that same shipment can degrade more rapidly than one traveling 500 kilometers if it crosses too many dew points. The real enemy is not the number on the thermostat, but how often that number dances across the dew line. Each crossing pulls moisture from the fish's surface, deposits it on the inner packaging, and reintroduces it when temperatures dip again. It's not the journey, it's the rhythm of that journey. And that rhythm can now be predicted, not with guesswork, but with data. Predictive transport software has become the new silent driver in smoked fish logistics. These systems simulate condensation stress maps using a matrix of environmental variables, historical climate trends, container insulation profiles, internal air circulation modeling, and even micro-vibrations. With this data, logistics managers can foresee where a condensation risk might occur, not based on temperature alone, but based on thermodynamic pressure, route topology, and container response. It's no longer just about maintaining cold, it's about anticipating stress. Think of it as transporting a precision lens across a bumpy road. The lens might be protected, cushioned, even stabilized. But if the internal alignment is disturbed by microcondensation or fine vibration, the optical system loses calibration, even if it looks intact. Smoked fish logistics work the same way. The product can appear sealed, unspoiled, even cold. But if the internal moisture migration wasn't managed, the damage is already done. The equilibrium is lost, and no amount of external refrigeration can recover what was misaligned during transit. So, what really moves these 5 million tons every year? Not ice, not diesel, not just insulated walls. What moves them is foresight, calculations made before the truck leaves, decisions informed by maps of invisible thresholds. The journey of smoked fish is not a passive one. It's guided, predicted, and constantly recalibrated by physics in motion. And in this chain, stability is not a condition, it's a behavior. One that can only be achieved when every element, from curing to condensation, is treated as part of the same continuous equation. Before we continue, take a second to check the pinned comment. If the behind the scenes of smoked fish transport fascinates you, there's something there you'll want to see, especially if precision and logistics are more than just passing interests. From the outside, 2 pallets of smoked fish can look identical. Same weight, same packaging, same origin. But open them at destination, and the story may differ completely. One pallet remains pristine, its fillets firm and dry, surfaces intact. The other carries a veil of surface mold, softened texture, and signs of condensation. The cargo wasn't mishandled, it wasn't delayed. So what happened? The answer lies not in temperature, but in airflow. More precisely, in how that airflow interacts with the geometry of the pallet itself. Smoked fish doesn't exude visible moisture like fresh catch, which makes it deceptively easy to overtrust its resilience. But during transit, it still releases microscopic vapor through packaging microperforations or from the space between fillets and the vacuum seal. That vapor doesn't just vanish. It behaves. It moves. It seeks balance with the surrounding air. And when the design of the pallet ignores the vertical vapor pressure that builds between layers, it creates microclimates, tiny, stagnant pockets where moisture condenses, nutrients become exposed, and fungal spores find the ideal conditions to thrive. These pockets are not accidental. They are engineered by omission. This problem is magnified by packaging assumptions. Because smoked fish is partially preserved, many exporters use rigid, non-perforated crates or apply plastic liners that restrict airflow entirely. The result is a lack of passive cross-ventilation, no lateral escape for the rising humidity, no channel for thermal dissipation. The load becomes its own insulator. In refrigerated environments, that insulation traps differences. A small delta in ambient temperature quickly becomes a vertical gradient across the pallet. And in logistics, gradients mean risk, not always visible, but always measurable after arrival. Inside the container, the air moves in programmed currents, guided by ducts, calibrated to circulate cold air from floor to ceiling. But these currents require a counterpart in the load. Perforations, spacing, and structural alignment that allow the cold to flow, not bounce. If the base of the pallet is too low, if the crate design ignores undercurrent circulation, or if the outer surfaces are too smooth, they deflect the airflow instead of distributing it. The result is turbulence, small, invisible eddies of warmer air that settle near the bottom of the load and trigger condensation exactly where it's hardest to dry. Engineering has already offered answers to this. In Northern Europe, a group of smoked fish exporters redesigned the bottom structure of their pallets. They lifted the product layer by just 3 centimeters. That small elevation created a flow channel wide enough to eliminate the turbulence dead zone beneath the load. The result was measurable, a 12% drop in product loss over a year of shipments. No change in temperature, no change in speed, just structure. To understand why this works, return to the field. Think of a tractor with a blocked radiator. The engine runs, the gears engage. But without airflow, heat accumulates slowly until performance fades, or worse, the system fails. The smoked fish pallet behaves the same way. Its failure doesn't announce itself with alarms. It creeps in with imbalance, with moisture that cannot leave, with airflow that cannot enter, and with microorganisms that only need a single hour of stability to begin their expansion. This is the overlooked side of food logistics, not the large numbers, not the horsepower, but the design decisions hidden in the base of a pallet. Decisions that don't seem mechanical, yet govern the mechanics of preservation. Because in modern agribusiness logistics, airflow is not a suggestion, it is a vector of survival. And when ignored, it becomes the silent contaminant that moves without ever being seen. Every shipment of smoked fish is more than a product on the move. It's a system in equilibrium, one that must be preserved across thousands of kilometers through climate shifts, mechanical vibration, and microscopic moisture changes. What seems like a passive journey is, in reality, a finely tuned response to variables most people never consider. Time, airflow, and container architecture act not independently, but as interdependent forces in a dynamic preservation equation. In this equation, cold alone is not enough. Precision matters. Just as grain silos use adaptive fans to adjust airflow based on real-time humidity levels, smoked fish containers could shift from fixed refrigeration to responsive systems. It's a lesson borrowed from the field, where machines no longer just operate, but adapt. This level of control transforms the cold chain from a static shield into an intelligent buffer, capable of correcting itself before damage occurs. That future is already being tested. Logistics providers like DHL have deployed smart boxes, sensorized containers, first used in pharmaceutical transport. Now these same systems are repurposed for smoked fish exports, especially in ports where infrastructure is unstable. By tracking shock, humidity, and thermal fluctuations in real time, they don't just store data, they provide early warnings. They act. In a chain where a 2-degree imbalance during a customs delay can spoil a full load, this kind of foresight is no longer a luxury. It's essential, and the impact reaches far beyond fish. Fruits, vegetables, seafood, even live animal transport stand to gain from what smoked fish logistics have already revealed, that perfection lies not in insulation, but in reaction. A container must now behave more like a greenhouse on wheels, where systems don't just preserve, but respond, where the cargo isn't just cold, but protected by anticipation. What smoked fish teaches is that in the silence of a sealed crate, a complex choreography unfolds, one that involves physics, engineering, and human ingenuity, one that doesn't just keep food fresh, but keeps the global supply chain alive, quietly, precisely, and always in motion. And while you're here, take a moment to check the pinned comment. There's something there you won't want to miss.